Hello and welcome. This is Terrence Fagan, and this video is going to discuss more on 2D example problem. This one has a spring associated with it. Some students get a little bit confused when they talk about springs, but furthermore, this will also be a two-part series, trying to make sure these videos are nice and shorter than the previous ones. So with that, let's start with this. So basically we have this lamp being pulled down by the force of gravity with some mass. There's a ring up here connecting this line AB, and line AB actually has a spring in it. And then also connecting a line AC. Now, it says it wants to determine the length between A and C. How would we get that? So first we'd have to figure out the forces, and that's what we're going to first find out in our part 1 series. And then in part 2, we'll discuss how to get the rest. But let's set up the problem. So we're given the illustration. Then we're given A is equal to 2 meters. Theta is equal to 30 degrees. K, the stiffness, is equal to 300 Newton per meter. The mass is equal to 8 kilograms. And we want to find the length of AC. Oh, we're also given the undeformed length, so we're going to put that up here in lowercase AC, and I'm going to put AC as a little prime there, and that is 0.4 meters. Again, this thing is stretching, so this is the initial one without its deformed, but because there's a force there, we want to determine the unstressed length as well. So let's draw a free body diagram, and we're going to illustrate that down here. And what we're going to do is draw a free body diagram just concentrated on at A. And let's take a look, and this is known as a particle free body diagram. We're not drawing much of anything else. So first and foremost, we can say that ring, we can say, hey, that looks like an A. That ring here, we can say that that's just a point. I'm going to put this in colors, and we're going to put the weight of this going vertical down, and let's see, the weight, we could solve this right here, is equal to mg, and we're going to use 9.8 for this, and the weight is actually approximately 78.5 newtons. Furthermore, let's look at the reactionary forces. So the reactionary forces, we have one force here. That's the force of AB. And then we have another one, the force of AC. So all of these are relevant. But what we know is, and we also know a little bit more information, so what we can do, our free body diagram, is put in a theta there, and what I'm going to do is I'm going to put also a coordinate system on here. So this is important. So notice that it's a particle and it's about a point. So we had all of these forces are congruent or converge at point, and we're going to label this A. So there's no need to do moments. That means that in our solution, two general equations we use are sum of the forces in the x direction equal to 0, and sum of the forces in the y are equal to 0. So that's this is the first step. So the first step, determine forces. So how do we do that? Well, we know, and which order do we put? That's always a kind of a question. We'll put a box around here so we can move down and move down here. Which one do we use first? Well, if we do the sum of the forces in the x direction, we're left with two unknowns. But if we do the sum of the forces in the y direction, that will give us FAC. So, or FACY. So let's do that. So we have the sum of the forces in the y direction is equal to 0. So we have the force of AC times, remember that this one is, so it's the times the, this, in this particular case, this is has a theta here, so you can, it's better to use sine and theta rather than these ratios. It's not given any ratios. So in this case, it's force of AC times the sine of theta, and that's going in the positive direction. So if we break that down, these components down, we have this direction, we have this direction. So this is FAC X and FAC Y. So furthermore, we can say that we also know that this is in the positive, and then this gets this minus the weight. So that gets equal to 0. So if we look at that and we do everything, we can say that the force of AC is equal to the weight divided by the sine of theta. And we come up, and we know a couple things. One thing is we know it's going to be greater than 78.5, mainly because the sine is always less than 1. That makes that, the FAC, greater than this W. And if we do that, we know that we can figure out that it's going to be equal to 157 newtons. So that's it with FAC. So we got FAC, so we can circle this. We know the weight. We just have to find FAB now. And then we're partially there. Not done with this problem, but this is, we'll be done with part 1 in a second. So we go with the force of, sum of the forces in the x direction is equal to 0. And we can say that negative FAC, now we know that, and times the cosine of theta plus FAB is equal to 0. So we got our directions right. Now, if you ever run into a problem where if you put this in tension and all of a sudden you have a negative value, you're going to cross this out and then further change the sense of the vector. So if we continue this, we know that the force of AB is equal to the force of AC times the cosine of theta. Furthermore, we know that it's going to be less than 157 because cosine is always less than 1, and whenever you get a number less than 1 multiplied by a number, you're always going to get it less than. So with that, we can find out that it's going to be 135.9 newtons. So now we're on a track to start to solve for this, and we can, the next time we're going to isolate the spring, and then we're going to find the information in the spring to let me know that the distance between A and B, knowing that, and then we can find out from that information, we can find out what the length of C and A, or between C and A. So good luck, have fun, and see you soon.